All right. Well, it's my pleasure to introduce Kosta Plakas today for today's Journal Club presentation. For those of you who may or may not know Plakas or Kostas, I'll give you a little intro. Kosta contacted me probably about a year and a half ago, where he was working in the area and as a not a postdoc, but in a pharmaceutical company. I think he was doing antibody drug conjugates, and he wanted to get back into something that was a little bit more exciting, and he wanted to get into the imaging field because he had exposure to that early on. He did his undergraduate work at SUNY Stony Brook, and he was highly influenced by a presentation from, I think it was it Joanna or Nora?
Dr. Joanna Fowler.
It was Joanna Fowler when she was at Brookhaven, and that introduced him to the world of PET imaging along the lines of what we're going to hear about today. He then went to graduate school at the University of Buffalo and got into imaging somewhat. I think your PhD project was on Raman spectroscopy, and a little bit different from what we do. But and then after the time in industry, he approached me, asked about a possibility of a postdoc position, and fortunate for all of us, Anna Rose and Julie had a slot available on the T32 Center, and he joined as part of that. And for the past 15 months, he's been working on developing radio tracers for the opioid receptor system. The first one that for those on the P30 have heard about it, we give updates all the time. It's we're making carbon 11 labeled mu opioid antagonist, and that's something that we hope to be ready to take in the non-human primates in the very near future. And then he also has a delta agonist project that he's working on. But I think today's Journal Club kind of came out of his T32 project, and making a radio labeled antagonist to take the place of carbon 11 carfentanil, and it's right up the line of what we're doing with our non-human primate imaging studies on the Explorer. So I think this presentation is a good blend of all the things that are going on in the Mac lab and on the P30 related to mu opioid receptors, and particularly with respect to carfentanil and non-carfentanil. So this I think is going to be a very important Journal Club presentation, because it sets the stage for a lot of things we hope to do in this coming year. So with that, Kosta,
very good. Thanks,
very interested in hearing this report on this paper.
Thank you, Bob. And Kosta, go ahead and plunge in.
Thank you very much for the warm introduction. Can everybody hear me?
We hear you fine.
Okay, beautiful. So let's get right into it. First, thank you all for taking time out of your day. I know it's the summer, some of it's travel. It's not a particularly nice summer day today, but nonetheless, thank you for taking the time to come and listen to this discussion. I think it's certainly an important topic as we find ourselves, to borrow a term from a previous P30 discussion, in the synthetic opioid era. So here's just a brief outline for the discussion today. I realize we all come from somewhat diverse scientific disciplines, so I thought it would be a good idea if we had a little bit of context, if I laid a little bit of groundwork to enable us to understand the topics presented today. Let's see, can everybody see my laser pointer? I think that is a yes, hopefully. So we'll spend a little bit of time. I'll just briefly mention the chronological development of opioids. I find the history quite fascinating, especially as it pertains to some of the developments that led us to the opioid epidemic as we know it today. We'll talk briefly about the characterization of opioid ligand and opioid receptor binding, both at kind of a systems level and also a receptor level. So thinking big and small, how the small molecules interact with proteins of interest, and how that in turn can lead to various different pathological states. We'll then talk a little bit about the authors, the reason that they chose to undertake this study before diving into the article at large today. If at any point you have anything you'd like to add, by all means, please feel free to interrupt. I think these things tend to work out when we can have a lively discussion. So just to reiterate, if you have anything you want to add, questions, comments, concerns, or bitter remarks, feel free to interrupt and add your 2 cents. So we'll start with a little bit of a timeline. So opioids, as many of us probably know, are an extremely old drug class. I don't have an exact date for when they first became known, but they probably predate written history. I've definitely read some reports from like the Byzantine Empire, where opium plants and their primary constituents, opiates, so opiates are the naturally occurring opioids, were used in various different forms or elixirs to elicit, pain relief. And most of the opiates and opioids that are derived from this plant relate to or are structurally similar to this morphinan scaffold, which I've highlighted in blue. So there are 3 sort of fused rings with this one ring coming out of the plane of the page sort of towards you. And most of the compounds that are responsible for the opium plant's activity belong to the class known as an alkaloid. So it's a cyclic compound with at least 1 nitrogen that is basic in nature. So it possesses a lone pair of electrons, if you will. So up until fairly recently, in the grand scheme of things, opium and opium plants were kind of consumed at whole. So you can, kind of make them into different elixirs, and you can also break them down into individual constituents. It wasn't until roughly the early 1800s, we'll say about 1803, where morphine was first isolated by, I believe, a German chemist. And it was, I think, synthesized properly in 1805. It continues to remain kind of a staple or a benchmark that synthetic organic chemists will use to test their synthetic skills. So some fairly well-known chemists have tried their hand at this. K.C. Rice, Trost, a couple of others have certainly tried to show their synthetic efforts in making this compound, and it remains probably one of the most prescribed analgesics known on the market. I skipped a couple of years here. I'm sure there was a lot that took place between the 1800s and we'll say mid 1950s, but in 1961, I think it was Daiichi Sankyo was a company that first synthesized one of the first known antagonists. So morphine is an agonist. It acts on the opioid receptor to elicit a response that is an anti-nociception response. Naloxone being an antagonist and its counterpart naltrexone, they act to preclude the binding of an agonist. And so these were brought about. Naloxone, I think, was first approved in 1971. Naltrexone a couple of years later in 1984. And again, these represent some of the first antagonists to hit the market. Where things start to pick up speed as it leads to the course with the opioid epidemic that we find ourselves in relates to a company known as Purdue Pharma. And what they were able to come up with was a formulation of morphine known as MS-Contin. So if you're not familiar, MS stands for morphine sulfate. Contin is continuous, and so it's approved for treating chronic pain in 1984. One of the key reasons that they were able to obtain approval is that they reasoned that the continuous release capsule or coating that this pill possessed was supposed to limit the kind of crests and troughs of the drug profile as it's metabolized. And as we'll see, that's only kind of about half of the picture. But nonetheless, they were able to get approval for this drug in 84. A few years later, about 11 years later, which interestingly coincides with when the patent on MS-Contin was up, they, meaning Purdue Pharma, was able to get approval for OxyContin. And you can see that all of the agonists and antagonists they've shown so far contain this scaffold that relates to the morphinan scaffold. In, I think, about 2013, maybe a couple of years before, a company by the name of Insys Therapeutics, they developed a fentanyl lollipop, and it's primarily approved for end-of-life care. So patients suffering from pain associated with end-of-life cancer. Fentanyl also becomes a little bit more prevalent as a street drug. So this is derived from morphine, and that you just replace the 2 OH groups here with this acetyl group. So heroin is also referred to as diacetyl morphine. But it's interesting. as we start moving into the synthetic opioid era, there is kind of a shift from this 3-ring scaffold to fentanyl, which has somewhat more of an elongated structure. And we'll see in the coming slides what that means for the ramifications of its potency. And most recently, as most recent as last year, the FDA approved Clexato, which I believe is an 8 milligram intranasal formulation of Narcan. And Narcan is the antidote, of which the active ingredient is naloxone. If anyone's interested in further reading, I highly recommend this book, Empire of Pain. It's a journalistic account that kind of more or less what I base this timeline on. You might be able to get it at the library, or if you're interested, just let me know. I'd be happy to let you use my copy. So now that we have kind of a chronological development of how we've gone from morphine and classical compounds to the synthetic opioid era and synthetic opioids and how they're different, let's look a little bit about their mechanism of action and how they elicit their response. So mu-opioid receptor activation is indeed an attractive target for analgesia. Per the most recent CDC statistics I found, about 1 in 5 or 20 million adults suffer from chronic pain. Whether or not it's a good idea to treat chronic pain with an opioid, we'll see that's not such a good idea in just a couple of slides. But as many as 1 in 8 suffer from high impact pain, and we can loosely define that as pain that interferes with someone's daily life. These small molecules bind to a G protein coupled receptor. In this case, the opioid receptor. They bind on the extracellular side, on the N terminus. And this is a fairly complex graph, but just kind of an overview is that mu-opioid agonists can do about 2 different things. They can elicit G protein coupled signaling, and this is thought to be responsible for analgesia. But they can also engage in beta arrestin 2 recruitment. And the prevailing hypothesis is that that is responsible for respiratory depression, which is likely the key driver in mortality in opioid overdose. The mu-opioid receptor is located in the central nervous system in the brain along the spinal cord. And also your nociceptor is kind of in your peripheral nervous system as well. Because of the proximity of the mu-opioid receptor to the reward center of the brain, there can be what's known as like a learned association between receipt of the drug and pleasure, and almost what's known as a Pavlovian conditioning. And so repeated receipt of the drug can strengthen this connection, and this can lead to obsessive thinking about the drug, erosion of inhibitory control over efforts to refrain from taking the drug. And this is sort of where the nasty claws of addiction can start to take effect. And so therefore, I would argue that the benefits of treating chronic pain with opioids are questionable at best. There are a few other physiological events that can happen as a result from exposure to opioids and chronic exposure to opioids. So repeated exposure can lead to down regulation of the mu-opioid receptor in a process known as tolerance.
Yes. So the immediate crisis is passed. So, but I still would like to know.
I think someone probably needs to mute their, please
we
mute.
were, our research scanner went down.
Janet-
and so we were trying
Janet
to.
Redden, can you please mute your microphone, and George Woody and others? Thank you.
Thank you very much. So repeated opioid exposure can lead to downregulation of the mu-opioid receptor. This process underpins tolerance, where you'll need a larger dose to achieve the same measure of analgesia. And this can be a leader to dose escalation. And also paradoxically, repeated exposure can lead to something called opioid-induced hyperalgesia, which can leave a patient in chronic pain. And so I just want to make sure that the distinction between tolerance / dependence is known, that there's a difference between tolerance dependence from addiction. So there are 2 or 3 separate processes that can happen. Tolerance and dependence is thought to be a bit more of a shorter term result, where addiction, not addition, addiction is thought to be more of a long-term process that takes place. One thing I find fascinating is that both opioid agonists and antagonists that act on the mu opioid receptor share some conserved interactions. So here we have, just for reference, the morphinan scaffold. And if we look at, in this case, beta-phenyltretsamine, this is an irreversibly bound antagonist where there's a covalent bond formed between the lysine residue and what was an alpha-beta unsaturated ketone. There is a conserved interaction between this positively charged nitrogen and aspartate 147. And so we'll see that here.
What?
We'll see that in synthetic agonists such as Damgo.
Folks, please mute your please mute your microphones.
Thank you very much. Unless that ice cream was meant for me, in which case I would love an ice cream. We also see this conserved interaction with biased agonists. So this is what I would call a second generation biased agonist. And these are thought to preferentially activate G protein coupled signaling and therefore analgesia over beta arrestin 2 recruitment. I think to date there's one clinically approved through Truvina, and that molecule is called aliceridine. And just to, again, to reiterate, the interaction between the aspartate 147, which we see here, and a positively charged nitrogen is seen amongst all of these classes. Interestingly, synthetic opioids such as fentanyl, they do share this conserved interaction. So often these are prepared as like a salt, where this would be positively charged, or physiological pH, it's probably positively charged anyway. But we see a similar interaction, right? Here's kind of a zoom in of this interaction that we see. But what might be responsible for the longer residence time and or higher potency of these synthetic opioids is that it's thought these can move deeper into the binding pocket and engage in a similar kind of bond with between histidine 297. So again, the synthetic opioid having a bit more of an elongated structure can move in deeper and form a this pseudo/transient bond here. And it's hypothesized that that's one of the reasons why some of these synthetic opioids have such a high potency. So with these kind of tools at our disposal, let's move into the paper at large. This paper would have what I would say is kind of an all-star team going for them. The first author is Dr. Yana Kang, who is an assistant professor at Howard University. Interestingly, she's in the Department of Mathematics, though I checked out her CV and it turns out she's held research positions in radiology before. I think that makes sense after having read the paper because there's a lot of elegant mathematical modeling that takes place throughout the paper. Sungwon Kim is, I believe, a radiochemist who's been in Nora Volkow's group for quite a while. He likely took the lead on the synthesis of the radiotracer, and for today, that's going to be a C11 carfentanil. Also in the paper is Dr. Joanna Fowler. I was kind of surprised to see this just because last I checked, she was a scientist emeritus at Brookhaven National Lab. And as Bob alluded to, I had the distinct pleasure of listening to one of Dr. Fowler's lectures when I was but a wee lad, a wee freshman, freshman undergrad Chem, long time ago in a galaxy far away. And her husband, Dr. Frank Fowler, actually taught me organic chemistry. Here is Dr. Joanna Fowler winning the National Medal of Science from then President Barack Obama. And last but certainly not least, we have Dr. Nora Volkow, who is the director of NIDA, a position she's held, I think, for at least 20 years. And Dr. Fowler and Dr. Volkow have really become powerful voices and key opinion leaders. It's sort of the reclassification of addiction as something that can be treated and something that deserves our utmost attention. So let's dig into the paper. And again, should you have any questions or comments, we can certainly liven this up with some discussion. But the study rationale, or the reason I think this paper, or the studies in this paper were undertaken, stems from a clinical observation that originally was published in this Morbidity and Mortality Weekly Report, which was published in 2017, but it details the events of a June night in 2016. And so we'll just open this up with a quote. Quote, some patients require doses of the opioid antidote naloxone exceeding 4 milligrams, where the usual initial dose is between 1/10 to 2/10 of a milligram intravenously. And several patients who were alert after receiving naloxone subsequently developed respiratory failure, which is, I believe, something that's unique to the synthetic opioid era. I haven't heard any anecdotal evidence that this is something that was seen with more naturally occurring, less potent opioids. It's not to say it didn't happen, but worth noting is that among 4 patients admitted to the ICU, 3 required endotracheal intubation for mechanical ventilation stemming from respiratory failure, and 1 actually required an intravenous drip of naloxone for a full 12 hours. So if we take a look at perhaps patient C, for example, we can appreciate that emergency medical services administered an intranasal dose of naloxone of about 3 milligrams, but then upon arriving at the emergency department, they were given an additional 4/10 of a milligram dose. And if we look at patient H, they received 2 doses from emergency medical services, 2 milligrams intranasally, 2 milligrams intravenously, and then required a continuous infusion for about 12 hours, which is pretty unique, and I would argue quite scary. So the tools that we're going to use to study the interactions between the radiotracer, which in this case is a very potent mu-opioid receptor agonist, C11 carfentanil, and the mu-opioid receptor, we're going to use positron emission tomography to do that. And I apologize, it looks like one of my equations sort of got jostled around it here. But the first study we're going to use is what's known as the displacement study. So we're going to administer a radiotracer, and we're going to define that as a time point as being time equal to 0. And then 15 minutes later, we're going to administer naloxone, which is the active ingredient in Narcan, and that is an antagonist. What we're going to do is we're going to use the PET scanner to observe buildup or radiotracer uptake. And we're going to use that to, 1, generate beautiful images, which we'll see in just a few slides, but we're also going to generate time activity curves, which you see before you now. In order to read these things, we can define some values and some acronyms. So we're going to use the standardized uptake value method, where our y-axis is going to be represented by SUV. And SUV, we can loosely think of as being the time-corrected activity of the radiotracer. So once we synthesize this thing, it actually starts decaying. The half-life of C11 is about 20 minutes or so. So we need a way to kind of account for its decay after it's synthesized, and furthermore, once it's injected. And we'll divide that value by the dose that we've injected and the weight of, in this case, the rats that we're using in this study. Part of using this method, the SUV method, requires the definition of a reference region. And this is usually a region that is going to be devoid of specific binding. In other words, this will lack the mu-opioid receptor. So they've defined the reference region as the cerebellum, and that allows us to get an idea of what the concentration of the free radiotracer and the non-specific binding is. And a hallmark of that is we'll see rapid uptake, but also rapid clearance of the tracer, indicating that it's not really sticking around to anything that it would bind to specifically. And that's in stark contrast to the thalamus, which is we've defined as a region of interest, which is actually somewhat rich in the mu-opioid receptor. So some things we can appreciate is that, again, in our reference region, we have rapid uptake, rapid washout, and that in our region of interest, our thalamus, will see rapid uptake, but we'll see that our baseline study, or our baseline ejection, and this is without any antagonists are added, there seems to be kind of a prolonged activity. And that's likely a result of some of the interaction between the radiotracer, C11 carfentanil, the opioid, and the opioid receptor. And just to reiterate, we're going to administer our antagonist at a time point of 15 minutes. And they've chosen clinically relevant doses. So they'll be using 0.035 milligrams per kilogram as one dose, and that equates to a human equivalent dose of 4/10 of a milligram. And they've also used 0.17 milligrams per kilogram, which equates to a 2 milligram human equivalent dose. So we can glean a lot of information from this. The first thing is that the clearance in the thalamus, right? So this is a region of interest. The time it takes to get from maximum uptake to about half uptake is 21.74 minutes for the higher dose, which I've delineated this red line, and 27.05 minutes for the lower dose. And also that prior to the injection of the antagonist, there is no significant difference between the baseline and different doses of the antagonist, indicating that any difference we may see is likely due to the competition between the antagonist and the radiotracer. And this difference is significant between this 21.74 and 27.05 minutes. So to reiterate, prior to injection of the antagonist, no difference. The higher dose of naloxone will reduce the specific binding of the radiotracer to the levels seen in the reference region. In other words, the cerebellum. The higher dose will do that in about 34 minutes. The lower dose will take 62 minutes, and this difference is significant. In other words, the antagonist competes with the C11 carfentanil and reduces the binding we see in the thalamus to more or less non-specific binding in 34 minutes for the high dose and 62 minutes for the low dose. And this difference is significant. There's another way we can kind of visualize this, and that is through the measurement or the calculation rather of an SUVR. And so this is standardized uptake value ratio, where we take the standardized uptake value of the target region, which again is the thalamus, and divide by that of the reference region, which is the cerebellum. So when the SUVR reaches unity or value of 1, the binding in the thalamus is equal to that of the cerebellum. In other words, all of the radiotracer binding we see in our region of interest has likely been reduced to non-specific binding, and that there is a significant difference between the two doses in their ability to compete off our radiotracer that we're using. If we take a look at the rate of displacement of C11 carfentanil by naloxone, we can think of this as algebraically being a change in Y over a change in X. We see that the higher dose is capable of reducing the binding of the C11 carfentanil significantly faster than the lower dose, which is illustrated in, I believe this is figure 2D. And also of note, there is some displacement at baseline conditions as a radiotracer clears through either metabolism or radiotracer decay. The power of PET is that it can generate some really stunning and striking images. So what we're looking at here is in the top row is baseline conditions here, and then here and here. So all of these refer to times at which the radiotracer has been injected, but the antagonist has not. And in the baseline study, the antagonist will not be injected, but in these two studies it will. And so we can see statistically similar uptake is evident through these images for the radiotracer in these 3 cases. But we see statistical differences in the average uptake of the radiotracer in the post-naloxone injection scan. So for the low dose naloxone, we can kind of see that there's some difference in radiotracer uptake, but it seems to be a lot more pronounced with the higher dose of naloxone. Another study that was performed in this paper was a blocking study. So previously we were looking at displacement studies. Here, the order in which we do things kind of switches. So for a blocking study, we're first going to administer the cold antagonist. And so this is data from the supplementary information, where we're going to inject the cold antagonist at some time before, either 20, 40, 60, 87 or 180 minutes before our radiotracer. And we'll define the administration of the radiotracer as being T equals 0. Excuse me. And so we're going to do this for both a baseline study and then both the low dose and high dose naloxone. And what this allows us to calculate is the receptor occupancy, or how effective different doses of naloxone are in precluding binding of the radiotracer. So here we're looking at the mu opioid receptor occupancy of the antagonist, and it's modeled quite nicely by this formula. For anyone who wants a thorough derivation, this article does it, and they do it with mostly algebra. So it was simple enough for even a chemist, to kind of follow along. But the authors are keen to point out that it takes, or rather they're keen to point out that at 90 minutes, the high dose naloxone is still occupying about 60% of the mu opioid receptor, which is a significantly higher amount than the low dose, which occupies only 20%, or sorry, roughly 12%. And that this difference in occupancy is again significant. The authors were also interested in understanding about how long it takes for the receptor occupancy to decrease by half. So we can look at this if we look on the y-axis of our graph here, to get from complete blocking to about 50% occupied, or 50% occupancy by naloxone. It takes roughly 27.3 minutes for our naloxone to decrease in the low dose. And so you can think of that as the antagonist decreasing in 27 minutes, thus allowing a still circulating agonist to be able to bind. But for the higher dose, this time is actually much, much longer, a little bit over roughly three times as long. The time it takes for this receptor occupancy to decrease to about 50 is about 85 minutes. And again, this difference is significant. There are some really interesting PK and PD differences between each dose of naloxone. So I think they did this in a different set of mice where they used, I think they pulled different arterial samples over time to calculate the concentration of naloxone in the plasma as a function of time. And somewhat not surprisingly, there's a difference between the concentration of naloxone in both between the high dose and the low dose. So you can see the high dose reaches a much higher concentration than the low dose does. It seems to also take a longer time for it to clear from the plasma, which seems somewhat consistent with the findings we've seen before. They were also interested in calculating the minimum concentration required to reach about 50% occupancy. And that number is actually quite low. You only need about 0.2 nanograms per milliliter to occupy about 50% of the mu opioid receptors in the rat brain. But even though this is somewhat of a small or low concentration, the problem is that it seems to clear quite rapidly from the system. So both doses, the high dose and the low dose, seem to reach and surpass the 0.2 nanograms per mil required to at least saturate 50% of the mu opioid receptor. But there seems to be a time-dependent decrease, or rather dose-dependent decrease in the concentration as it's cleared. And to reiterate, the low dose clears quicker than the high dose does. This finding more or less suggests that 2 milligrams of naloxone may be insufficient, or 2 milligram human equivalent dose of naloxone may be insufficient or incompatible with preventing quote unquote re-narcotization that's seen with some of these synthetic opioid derivatives, which are postulated to have a longer residence time and longer circulating half-time. The authors point out that some literature suggests that the circulating half-time of fentanyl and related derivatives can be as high as about 7 hours. So high-dose naloxone is, a good way we can sort of combat that, underpinning and supporting the FDA approval of high-dose Clexato, the 8 milligram or so intranasal formulation of naloxone, but we may need to look somewhere else to get either more potent opioid antagonists or ones with a different PK/PD profile, but perhaps maybe different K-on or K-off rates. But that also kind of brings to light a question that really potent opioid antagonists could bring about precipitated withdrawal quicker. And so that's certainly a limitation that we can open up to discussion. But to summarize, it appears that naloxone can and does displace carfentanil in a dose-dependent manner. And we see that higher doses of naloxone occupy the opioid receptor longer, which could perhaps minimize the occurrence of re-narcotization or having patients be aware and then slip back into respiratory depression. And I certainly think the data presented in this paper corroborate the findings, or the findings in this paper corroborate the decision by the FDA to approve high-dose naloxone as we expand our repertoire of tools to combat synthetic opioid overdose. That said, there are a couple of limitations in this study that are certainly worth mentioning, and I think the authors are pretty transparent in pointing that out. First and foremost, the study only includes male rats, and there are numerous differences in the metabolism of these drugs that are present in rats, non-human primates, mice, and ultimately humans themselves. The one thing I really would have been interested to see is that respiratory depression has been seen using tracer doses of carfentanil previously. So I'd be curious to see if that was observed in this study using rats, and if that seemed to be minimized or reversed as a result of the administration of the antagonist. As I alluded to before, high-dose antagonists might work at de-narcotizing a patient and combating respiratory depression, but that could be at the expense of causing that patient to slip into withdrawal, which is certainly not a good thing. So there may need to be some intense pharmacological studies on determining what the right dose is per patient, or more so on like a patient per patient basis. And last but not least, I'll end with, I think the kinetics of naloxone may be incompatible with the synthetic opioids that might possess a really long residence time or clearance times upwards of a couple hours. And so with that, that's more or less all I had. I have some questions which we can look at, or if anyone has anything they'd like to add. I realize we have about 20 minutes left, so certainly plenty of time for discussion.
That was a really good tour of the opioid system, and also obviously this paper, which was really interesting because it really does parallel some of these clinical reports that you mentioned there and others that people have heard. When I think of a 7-hour half-life for some of the fentanyls, I confess I don't know all of them in terms of one versus the other, but that seems like 7 hours, you're going to always need even more than the 8 milligrams that was just approved, right? Because it's not going to go for 8 hours, that's for sure. So in your reading, or did you bump into a comparison of these fentanyls? Is the 7-hour version, I'm just speaking clinically, is that really common, or is that sort of pulling out something that's in the extreme? Do you know?
Yeah, so from my reading, I would think that's something a bit more on the extreme. What I'd like to do is kind of follow up with that computational study. And I'll backpedal here a little bit. Follow up with this computational study. I think they only looked at synthetic / fentanyl derivatives in its paper. And so one predictor might be if you have an opioid that can engage in sort of this deeper pocket interaction, that might be indicative of a longer interaction, longer residence time, but it also we might be able to use this to predict what antagonists might also display this property. So I should probably look at and see what papers may have cited this study to see if there's been any more recent clinical developments.
And of course, we're going at this with both barrels. One is to look at the potential for radio labeling antagonists that could be used as a tracer. The other thing is obviously the potential therapeutics of something that would be especially more potent, longer acting, and maybe, affinity being high enough to compete. And that's also something I haven't memorized, is the affinities of these antagonists versus these high potency agonists. Do you have any off the cuff comments on that?
Sure, I could tell you off the cuff, I think naloxone is an antagonist whose affinity is about 1, although I think it depends on which stereoisomer you're looking at. But that's also interesting is that the tracer that we're looking at today, C11 carfentanil, I think it's about 80 picomolar, but fentanyl is somewhere in the middle. So don't quote me, but I think about 400 picomolar. So there are differences in the potencies of these tracers, certainly.
Yeah.
I wonder what like the secret is for displacing a really potent agonist. Is it an antagonist with a similar potency, similar binding affinity? But that also leads us to the question of precipitated withdrawal. If you displace it too quick,
Which is, by the way, it's worth getting, I think Kyle and George are both on the call, some of their comments about precipitated withdrawal, because, you do want to bring people obviously back and reverse the respiratory depression. They often are in a very acutely upset state, right? Because they're thrown into immediate opioid withdrawal. It's kind of disorienting. And they usually don't come back and say at that moment, wow, I feel so much better now. I'd like to go to treatment. Often they feel so crummy and so overwhelmed with withdrawal that sometimes they want to just leave immediately and go out and seek an opioid. So it's a very tricky thing. And I think some of the people at Prevention Point could chime in on this. I don't know that they're on this call, but where they sometimes will reverse a person and then within hours, the person will be back again overdosed, and they'll reverse them. And it can be an extraordinary journey because of this sort of precipitated withdrawal and wanting to go right back out. So it is a tough hill to climb. George or Kyle, would you like to chime in? I saw you both on the call. You might be muted.
Yeah, I'm absolutely muted, but not now. Our thing about precipitated withdrawal is just getting people started on Suboxone. So it's a little bit different than the overdose situation. But yeah, precipitated withdrawal is definitely a bummer, and it definitely keeps people from wanting to get treatment. So.
And Kyle, this would be a great place for you or George to share the potential observation that you have about fentanyl being stored up for a long time and maybe slow released in patients who are undergoing opioid detoxification, and finding a precipitated withdrawal where you least expect it 7 days later. You want to tell a little bit about that? I think it would
let George talk about that. I think he's looked into it a little more extensively than I have.
George, are you still on the call? You're muted if you are. Let me see if he's still here.
He's there and he's still muted.
Okay. George, I think you're muted. If you want to share the episode of precipitated withdrawal with a patient who we thought would be well beyond having any fentanyl in his system. It's another clinical challenge.
Yeah, can you hear me now?
We can, George. Thank you.
Yeah. Okay. Yeah. The clinical problem may be best solved by looking at the length of time that the fentanyl stays in the system. I mean, the studies that you reported, and those are in the literature, are sort of acute studies where you look at antagonist X or agonist X and how long it stays. But in the clinical situation, you have people that are chronic users. It's not an acute situation like you get in surgery. You put you to sleep, they fix your heart, and they give you naloxone. You're out of it, and you're out of the recovery room, and you're fine. But the addicts, they're chronic users. Now, the fentanyl is fat soluble, and it hangs around. We've seen it. We're looking at it in the urine, quantitative urine tests. We're seeing it 8 days after they've been on a detox unit and have And the amount of fentanyl in the system is going down from 400 to 1,000 nanograms down to the 20s or 30s by day 8. But they still have a withdrawal reaction to a low dose of naloxone. So I sort of think the clinical problem is best solved by, first of all, trying to figure out the half-life of how long fentanyl stays in the system as a function of body fat and renal excretion, and go from there, because of that feature of the addicts. They're using 3, 4, 5, 6 times a day for months or years when they come to clinical treatment, and they come to the emergency room. You got the same situation. You overdose them, and they get precipitated withdrawal. They can be okay for a while, and then they'll go back into overdose because the fentanyl it takes a long time to get out of the system.
George, do you want to tell about the patient who had the very strong reaction that sort of helped alert you guys to this?
Oh yeah, this patient was snorting, inhaling street purchased heroin / fentanyl. I think it was mostly fentanyl, and he had a body mass index in the 40s. And we had him on a detox, and he was doing fine. His cows and the sows went down. Come to day 8, looked like he was okay because his cow score was, at one point it was 9, but that was after he had an argument with a patient. And then 15, 20 minutes later, when he'd calmed down, it was 4. So we thought it was okay for naloxone, for naltrexone. So we gave him the naloxone challenge just to see if it was okay. And he went into a severe withdrawal at 8/10 of a milligram, and actually was transferred from the inpatient unit to the ER and given 3 or 4 or 2 to 3 liters of fluid. And he recovered it was all over about 10 hours. He went back to the floor, and of course he wasn't interested in naltrexone after that. And and then when we looked at his fentanyl index, fentanyl levels in the urine, it was like 440 or something when he came in, and it was, I think, 44 in the 40s when by day 8. Then we had a skinny patient, like body mass index in the 20s, low 20s, who went through the detox, got his naloxone 8/10 of a milligram, no problem, got his Vivitrol shot. And we had a couple others, not obese, but maybe a little bit more body fat than this one, came in with, and these were injecting, they came in with fentanyl levels above 1,000 nanograms, which is where the top limit that you get back from the lab. And they did okay for 8 days, nothing. And their COWS score went down into I think it was in the 40s or so, maybe even 20s. And we gave him 2/10 of a milligram of naloxone because we cut the dose from 8/10 to 2/10 as a starter, just because of our experience with the first patient. And they both had a mild withdrawal that lasted for several hours and went away, and they were okay. And they were discharged. Of course, no naltrexone, no Vivitrol. So, so we put it all together, and these are all people that had renal excretion above 90. That's the criteria for entering the study. So we know they didn't have markedly impaired renal excretion, but they did have markedly impaired impaired excretion of the fentanyl. And it seemed to be a function of their body fat index, because the 2 that got through that had the milder withdrawal reaction, the lower dose, were not severely obese. Their body mass index was probably the high 20s or low 30s. One guy had a low body mass index, did fine on 8/10 of a milligram. That was fine. And then, of course, we had the first one that really caused a little PTSD in me, I think, because I gave him the naloxone challenge. And
Wow.
and that made us change our procedures so that we did it. But in the 2 that had the mild reaction, the fentanyl was still on board in the I forget what it was, in the high 20s or low 30s. And it came, and they were injecting, and they came in at levels of 1,000, above 1,000 nanograms or above. So That's the way we're.
It's a very, I mean, it's a very interesting clinical situation. And
Yeah.
George and Kyle's study is actually trying to help people through detoxification with the goal of getting onto depot naltrexone. But in order to be given depot naltrexone, they have to pass the Narcan challenge, the
Yeah.
naloxone challenge. So that's why the day 8 injection is sort of the do or die. Are you ready to go? Are we ready to go? Can you? And then if somebody has a really bad experience, of course, they're not going to probably proceed to take the naltrexone. They
Yeah.
can't. So there we are. And so I think you guys are thinking about writing this up as a manuscript, or maybe you already have.
Little case reports. I've been working on the
Yeah.
chapter that's taking a huge amount of time, and I'll get to that when I finish this.
Right.
But just as an addition to that, we did a study in the Philadelphia prison before fentanyl came on board and before COVID came on board. We stopped that a couple of years ago. And we didn't have any precipitated withdrawal except a couple patients that were using buprenorphine. It was available in the prison, and we weren't testing for it. We started testing for it, and then didn't start. A couple patients that tested positive for bup, and we didn't give them the naloxone challenge. We just waited until they had it out of their urine, and they were fine. We gave 0.8 milligram to, like, I don't know. We had about like 70 patients or so in that study. And no precipitated withdrawal from the prisoners, because
Yeah.
it's a lot different than, and of course, no fentanyl around at that time.
We're in the fentanyl era. I mean, one of the things that's really fun about the things that you're working on in your projects, Kosta, in Bob's group, is that, this will be obviously a huge tool for the field. To have an antagonist will be a lot easier to work with than obviously C11 carfentanil, which is so high potency that we have to have a lot of safety procedures in place just to make sure that, when we're making it, nothing goes awry. And also, as you said, in small framed people, sometimes you can even see pharmacologic effects of carfentanil at tracer doses. So being able to have an antagonist tracer would be a huge thing for the field of research. We just haven't had that tool in any good way for all of these years. And of course, you can hear from the people who work on the clinical side and the clinical research side is that there's something really challenging about this fentanyl era in terms of basically being able to get people through detoxification, get them onto naltrexone, and also just keep them alive. So I think there's going to be a huge opportunity for research and clinical opportunity for the path that you're on.
This problem is it's a really serious problem if you're trying to get them on a narcotic antagonist, on Vivitrol. Not as serious a problem if you're trying to get them on the buprenorphine, because you have some agonist effects with the antagonist effects. But you still have, we've had patients come in and for our study we worked up, and I asked them if they've taken buprenorphine on the street, and a couple of them told me that they had tried it and they wouldn't take it again because it threw them into withdrawal. So you are seeing that. But NIDA has a large emergency room study trying to get people on the Vivitrol, and they don't seem to be having a huge problem, except at the Philadelphia site. This is just hearsay. And of course, we're the center of fentanyl. We're like fentanyl central here in Kensington, I think. So it varies. The content of fentanyl and the supply varies according to where you are, where you're buying it. But here in Philadelphia and down in as far as in Wilmington, the heroin supply is really highly contaminated.
And Philadelphia used to just be proud of the fact that they had the most potent heroin.
Right.
Strange thing to be proud of, but Philadelphia always had one of the most pure heroin sources. But it's been pretty much completely replaced by fentanyl. I think on the street, virtually, all the so-called heroin use that's going on when people come in, and Kyle can attest to this, that when they're looking at urines, you're seeing people who are fentanyl positive, but are heroin negative. So it's pretty much replaced street heroin. So even if you think you're taking street heroin, or you're injecting a white powder or crunched up pills that are purporting to be OxyContin, you will be probably using fentanyl in an unknown dose, which is way beyond Russian roulette. So the path that you guys are on with these antagonists sounds very exciting, and you've got 60 of them now. 60 of them.
No, that was yeah, right now we do in our study. Yeah.
But and I was saying that Kosta, they're making 60 compounds. They have 60 leads that look like antagonists behaviorally, and they're looking like, some of them look, you said, very promising, Kosta.
Yeah, some of them have higher binding affinity, or more potent binding affinity than the GSK compound, which is pretty interesting. There's still a few other things we've got to figure out before we're, we radio label it, but it's exciting. Hope maybe by the Penn Pay State presentations we'll have something. I don't want to promise, but we'll see.
Sounds like a wonderful hot summer. Anybody have any other questions or comments? Anybody? I know Jake Dubroff is on the call, and he had the experience of working with carfentanil before and is preparing to do it again. Jake, you want to comment on the pleasures of working with carfentanil as a tracer and how much you look forward to having an antagonist treatment?
Yeah, I have my full confidence in Sharon and the cyclotron staff in having high potency and low mass, and I'll trust in them, and I'll have some Narcan on me for all the studies. But I think that what in some ways it's going to be for me a little bit easier this time, because the last study that I did, it was a bolus plus infusion. So I had to take the C11 20-minute half-life and split it in half and give half as a bolus and half as an infusion with the subject on the PET scanner. So just measuring the right amount and giving it as a total bolus, I think will be plenty, but less than it was. So I think just knowing that mass is, making sure we're under, I think the 0.03 micrograms will be good. What I was thinking about from the clinical scenario, and I just there was a comment about macrodosing. So I don't know if anyone wants to speak to that, but it seems like we're confounding a couple clinical scenarios that obviously Kyle and George are familiar with. And the one I know, because I'm not an addiction psychiatrist, I just was an intern in Philadelphia and watched a couple people literally raised from the dead with Narcan, is I think this data and the timing is how fast we get it there and how fast we can make sure that we're no longer suppressing these overdoses respiratory drive. And then you have this bridge to get them to a place where you can agonize the receptor so they don't go into withdrawal, but they aren't abusing the drug. And so I think, but having a radiotracer antagonist that's easier to deal with than carfentanil could obviously permit us insights into those scenarios. But I don't know. I guess deferring to both George and Kyle, you guys probably have seen it in more the chronic phase, and someone in the ED maybe in the more acute phase. And so I think there's a kind of a bridge there, and getting someone who's obviously using and convincing them to participate and getting them to treatment. So maybe that's the time can be kind of the unifying factor here. That's what we're looking at as a variable.
Thanks, Jake. Anybody else have any comments or experiences that they would like to share? Bob, any comments on the path?
Yeah, I think, just based on some of the discussion today, being able to do the whole body imaging studies on the Explorer can help tease out some of these central versus peripheral mechanisms. I think right now you could probably build a whole research program around whether or not there's buildup or depot effects of these fentanyl analogs that lead to prolonged occupancy in the brain based on body mass index. I mean, you could design a whole research project around that, looking at the type of studies that Kosta presented today, looking at tracer uptake versus displaceable binding by giving naloxone. So some of these things are, they're quite interesting. It's funny, I was looking at our whole body images when George was speaking, and we do see some slower washout from some organs like the spleen and whatnot, but our monkeys certainly don't have the body mass index of some of the people you see in the clinic. So we couldn't see any like generalized uptake throughout the body because they are, the monkeys that we imaged certainly don't have the fat content that perhaps some of the subjects you see are. But it's certainly something we can look at when we start our whole body explorer imaging studies in patients. We can see, how the distribution of carbon level carfentanil changes with respect to body mass index and whatnot. There's certainly some very valuable points raised today and things that we need to think about as we design our Explorer studies. But yeah, there's a lot to do. I think Kosta is sitting on a potential gold mine of compounds. We're characterizing his compounds from a variety of different ways, and we can look at them not only as tracers, but as a pharmacological tools to look at effects of competing with these fentanyl analogs. In our case, carfentanil, at the mu opioid receptor. So there's a lot of interesting stuff that we can and we will do going forward.
It's an exciting time, even though we've got a lake of fentanyl all around us. But thanks so much, Kosta, for bringing this to us today and giving us a good review. And thanks to everybody for the good comments. All right.
Thank you.
Until next time. Thank you. Have a good summer, everybody.